Hello there, and welcome to Science into Sleep. Tonight, let yourself settle somewhere comfortable, because we are going to drift through the quietest and most extraordinary story ever told. The story of space itself. Not the frantic, explosive version you may have heard before, but the slow, patient, almost impossibly gentle version. The one where stars take millions of years just to be born, where clouds of gas stretch across distances so vast that light itself needs centuries to cross them, where silence is not emptiness, but a kind of peace that wraps around everything that exists. Out there, beyond the thin blue edge of our atmosphere, the universe is unfolding at a pace that makes a human lifetime feel like the briefest flicker of candlelight. And every atom in your body was part of that unfolding long before the Earth existed. Tonight, we follow that thread home. If you enjoy these gentle journeys, I would be grateful if you liked, subscribed, or left a quiet thought in the comments. It helps others find their way here too, one sleepy soul at a time. But for now, there is nothing you need to do but rest. Let your shoulders soften, let your breathing slow, and let the universe carry you for a while. Now, let's begin. When you look up at the night sky on a clear evening, what you see is not simply a scattering of bright points against a dark curtain. What you see is depth. Every star sits at a different distance from where you stand, and every distance represents a different journey of light. Some of those stars are relatively close, merely a handful of light years away, and their light left home only recently. Others are so distant that their glow has been traveling toward you for thousands of years, crossing the silent gulf between solar systems long before anyone alive today was born. And between those stars, in the enormous dark stretches that appear vacant and still, there is something present, something patient, something waiting. The universe between the stars is not empty. It is filled very thinly, but very truly, with gas and dust. Most of it is hydrogen, the simplest and lightest element, the one that makes up roughly 3/4 of all ordinary matter in the cosmos. Helium, the second lightest, accounts for most of the rest. Together, they form what astronomers call the interstellar medium, a vast and wispy ocean of atoms and molecules spread so finely across space that you could travel through it for millions of kilometers and scarcely encounter a particle at all. A single cubic centimeter of this medium might contain only one atom. By comparison, the air filling your lungs right now holds roughly 25 billion molecules in that same volume. The difference is staggering. Interstellar space is among the best natural vacuums that exist. And yet, across the immense distances involved, where a single light year stretches roughly 9.5 trillion kilometers, even that faint mist of atoms accumulates. When enough of it gathers in one region, something remarkable begins to take shape. It becomes visible. It becomes something astronomers have named a nebula. A nebula is a cloud of gas and dust suspended in space, and some of them are enormous beyond easy imagining. A single nebula can stretch across dozens or even hundreds of light years, dwarfing entire star systems within its hazy interior. Some nebulae glow softly with color, lit from within by the ultraviolet radiation of nearby hot stars. Their light is often pink or reddish, the signature of hydrogen gas being excited by stellar energy and releasing photons as it settles back down. These are called emission nebulae, and they are among the most visually striking objects in the cosmos. Others shine not with their own light, but with borrowed brilliance, reflecting the glow of nearby stars and scattering blue and white hues like cosmic fog caught in a searchlight. And some nebulae are dark, dense enough to block the light of everything behind them, appearing as ink-black silhouettes against the glow of more distant regions. These dark clouds are not empty. They are among the densest and coldest parts of the interstellar medium, and it is inside them that the story of star formation most often begins. The process starts, as so many grand things do, with the smallest of changes. Within a nebula, the gas and dust are not perfectly evenly distributed. There are regions where the material is slightly thicker, slightly denser than the space around it. That difference can be tiny, a modest ripple in an otherwise smooth cloud. But gravity notices. Gravity always notices. Once a patch of gas is even marginally denser than its surroundings, it pulls on nearby material with a slightly stronger grip. More matter drifts inward. The density increases, and as it does, the gravitational pull grows stronger still, drawing in yet more gas and dust. A feedback loop begins, one that will not easily be stopped. What started as a whisper of imbalance becomes a slow, steady gathering of matter, a contraction that will continue for hundreds of thousands of years. This trigger can come from many sources. Sometimes the shock wave from a distant supernova, the explosive death of a massive star, ripples through a nebula, compressing regions of gas and nudging them past the threshold where collapse begins. Sometimes the pressure of intense radiation from a nearby cluster of young stars pushes the cloud inward at certain points. Sometimes two clouds drift together and merge, creating pockets of higher density where none existed before. Whatever the cause, the result is the same. A region of the cloud begins to contract under its own weight, rotating slowly as it does, and at its center, a new object begins to form. This object is known as a protostar, not yet a true star, not yet powered by nuclear fusion, but a growing ball of gas and dust that is steadily heating up as gravity compresses it tighter and tighter. The protostellar phase is long and quiet. Over millions of years, the collapsing core draws in material from the surrounding cloud. Much of this material does not fall directly onto the protostar. Instead, it spirals inward through a flattened disk of rotating gas and dust, an accretion disk that feeds the growing core gradually. The temperature at the center climbs degree by degree as compression converts gravitational energy into heat. At first, the protostar glows only in infrared light, invisible to the human eye, but detectable by telescopes designed to see warmth rather than visible brightness. It is hidden inside its natal cocoon of dust, a star in the process of becoming, shielded from view by the very material that is building it. During this gathering phase, something unexpected often happens. As material falls onto the accretion disk and spirals inward, some of it is redirected outward in narrow, high-speed jets that shoot perpendicular to the disk. These bipolar outflows can extend for light years, punching through the surrounding cloud and announcing the protostar's presence long before the star itself becomes visible. The jets carry energy and material outward, carving cavities in the dense gas, and sometimes triggering new pockets of collapse in neighboring regions of the cloud. It is a strange and lovely detail. A star that has not yet fully formed is already influencing the space around it, reaching outward even as it pulls itself together. Creation, it seems, is never entirely self-contained. Even in its earliest moments, a forming star is part of a larger conversation with the cloud that gave it life. And then, after millions of years of patient contraction, the temperature at the core reaches a critical threshold. The precise number is roughly 10 million degrees. At that temperature, the pressure and heat are so intense that hydrogen nuclei, single protons stripped of their electrons, are forced close enough together to overcome their natural electromagnetic repulsion and fuse. 4 hydrogen nuclei combine to form 1 helium nucleus, and in the process, a small fraction of their combined mass is converted into energy. That energy radiates outward as light and heat. One reaction alone releases only a tiny quantity of energy, but the number of reactions happening simultaneously in the core of a new star is beyond counting. Trillions upon trillions of fusion events occur every second, and together they produce an outpouring of energy so powerful that it pushes back against the weight of the star's own gravity. For the first time, the collapse halts. The inward crush of gravity is perfectly balanced by the outward pressure of fusion. The protostar stabilizes, and in that quiet moment of equilibrium, a star is born. There's no sound when this happens. Space carries no sound waves, no vibrations of air to mark the occasion. The star simply begins to shine, steadily, reliably, and without any sense of hurry at all. From this moment forward, it will continue burning hydrogen in its core for as long as the fuel lasts. And for many stars, that means billions of years. The balance between gravity and fusion pressure is so exquisitely fine that a star can maintain itself in a stable state for an almost unimaginable stretch of time. But the birth of a star is not only the birth of a light, it is also, very often, the beginning of a world. When fusion ignites and the protostar becomes a true star, the accretion disk that fed it does not vanish. Much of it remains. A broad, flat ring of gas and dust still orbiting the young star, slowly cooling and settling into a thinner, more orderly structure. Within this disk, something quiet and momentous begins. The tiny grains of dust, specks of silicate, carbon, and ice, each one smaller than a grain of sand, begin to collide and stick together. At first, the clumps are modest, no larger than pebbles. But as they orbit within the disk, they sweep up more material and grow. Pebbles become boulders. Boulders become objects kilometers across. And over millions of years, gravity takes over once more, pulling these growing bodies into ever larger formations. Rocky cores assemble in the warm inner regions of the disk, close to the star where temperatures are too high for ice and light gases to persist. Farther out, where the disk is colder, vast envelopes of hydrogen and helium gather around solid cores, building gas giants of tremendous size. Moons form in miniature disks around these new planets. Comets linger at the outermost edges, preserved in ice for billions of years. And gradually, the remaining gas and dust are either absorbed into the planets, blown away by the star's radiation, or scattered into the emptiness between systems. What is left, once the disk has cleared, is a solar system, a star surrounded by a family of worlds, each one orbiting in the plane of the original disk, each one carrying within it the chemical inheritance of the cloud that collapsed to form the star in the first place. Our own solar system formed in exactly this way, roughly 4.5 billion years ago, from a disk of gas and dust surrounding the young sun. The Earth assembled slowly from countless collisions of rock and metal in the warm inner region of that disk, growing from a formless cloud of particles into a layered world of iron core and silicate mantle, of ocean and atmosphere, and eventually of life. Every planet in every system traces its origin to a similar disk. The process is not rare, it is not unusual, it is one of the most natural consequences of star formation, and it means that wherever you find a newborn star, there is a reasonable chance that worlds are being built around it. The night sky is not only full of stars, it is full of places, most of them still hidden, still forming, still waiting to cool and settle into whatever they will become. Our own sun has been maintaining this delicate equilibrium for as long as the Earth has existed, burning steadily through an almost unfathomable supply of hydrogen. And despite the enormity of that consumption, it has enough fuel remaining to continue shining for roughly another 5 billion years. In the story of the cosmos, our sun is a middle-aged star, neither particularly young nor particularly old, neither especially large nor especially small. It is ordinary in the most comforting sense of the word, a steady light that has already outlasted everything that has ever lived on Earth, and will continue to burn long after the present age has passed. But not all stars share this quiet temperament. The universe produces stars across a remarkable range of sizes, and that range determines nearly everything about how a star lives and how it eventually dies. At the lower end are the red dwarfs, small, cool, and dim. A red dwarf might contain only a tenth of the mass of our sun, and it burns its hydrogen so slowly and so cautiously that it can persist for trillions of years. Because the universe itself is only about 13.8 billion years old, no red dwarf has ever run out of fuel. Every red dwarf that has ever ignited is still shining right now, somewhere in the galaxy, quietly going about its work. They are the most common type of star at the Milky Way. Estimates suggest that red dwarfs make up roughly 70 to 80% of all stars in our galaxy. Yet most of them are invisible to the naked eye, because their light is so faint that only telescopes can detect them at any significant distance. Proxima Centauri, the closest star to our solar system, is a red dwarf. It sits just over 4 light years from Earth, and has been burning steadily for billions of years. It will likely continue for billions more, outlasting our sun by an almost inconceivable margin. There is something deeply restful about a red dwarf. It asks for almost nothing from the universe, and in return, it endures longer than nearly anything else. At the opposite end of the scale are the blue giants and blue supergiants, stars of staggering mass and luminosity. A blue giant can contain 10, 20, or even 50 times the mass of our sun, and it shines with a ferocity that dwarfs smaller stars by factors of tens of thousands or more. The surface temperature of a blue giant can exceed 30,000 degrees, compared to roughly 5,500 degrees for the surface of our sun. That extreme heat gives them their distinctive blue-white color and drive fusion reactions at a furious pace. But this brilliance is purchased with brevity. A blue giant burns through its hydrogen so rapidly that its total lifespan might be only a few million years. A fleeting moment compared to the patient endurance of a red dwarf, where a small star sips its fuel across trillions of years. A massive star drinks deeply and is gone in what amounts to a cosmic afternoon. One of the most famous examples of a massive star in its later stages is Betelgeuse, the bright reddish star in the constellation Orion. Betelgeuse is not a blue giant any longer. It has already moved past that phase. It is a red supergiant, a star that has exhausted much of its core hydrogen and swollen to an enormous size as its outer layers expand and cool. If Betelgeuse were placed at the center of our solar system, its surface would reach somewhere between the orbits of Mars and Jupiter. It is a vast, aging star, luminous and unstable, approaching the end of its life. When it finally collapses, and it will perhaps within the next 100,000 years or so, the result will be a supernova, one of the most powerful explosions in the universe. But for now, Betelgeuse simply glows in the winter sky, a warm, deep orange point of light, patient and enormous, burning through its final reserves with the same quiet indifference that has carried it for millions of years. Between these extremes, the universe is filled with stars of every intermediate mass and temperature. Yellow stars, like our Sun, sit comfortably in the middle, burning steadily for billions of years. Orange stars, slightly cooler and smaller, endure even longer. White and blue-white stars burn hotter and brighter but live shorter lives. The color of a star is not merely aesthetic, it is a direct consequence of its surface temperature. Cooler stars glow red or orange. Hotter stars glow white or blue. This relationship is one of the most fundamental principles in stellar astrophysics, and it allows astronomers to estimate a star's temperature, size, and even its age from nothing more than the color of its light. Astronomers have organized this relationship into detailed maps of stellar properties, plotting stars by their temperature and brightness. When they do, patterns emerge that reveal how stars age and how they compare to one another. The most stable, longest burning phase of a star's life, the period when it fuses hydrogen steadily in its core, produces a clear band across these maps, and most of the stars you see in the night sky tonight are somewhere along that band. When you look up and notice that certain stars appear faintly reddish, while others seem white or bluish, you are observing this physics firsthand. A quiet cosmic code written in color across the darkness. The places where new stars are born are among the most visually breathtaking regions in the galaxy. The Orion Nebula, located roughly 1,350 light-years from Earth, is one of the nearest and most studied stellar nurseries. It is visible to the naked eye as a faint, hazy patch in the sword of the constellation Orion, and through a telescope it reveals itself as a vast cavern of glowing gas, illuminated by a cluster of young, hot stars at its heart. Inside this nebula, hundreds of protostars are forming right now, each one surrounded by a swirling disk of gas and dust, each one drawing closer to the moment when fusion will ignite. The light reaching your eyes from the Orion Nebula tonight began its journey more than 1,000 years ago, which means you are seeing the nursery not as it is now, but as it was in the distant past. And yet, the process of star formation within it is so gradual, so measured, that the scene has changed only slightly in that interval. Stars are born slowly. There is no rush. Farther afield, the Carina Nebula stretches across a region more than 300 light-years wide, making it one of the largest and most active star-forming regions in the Milky Way. Within it, towering columns of gas and dust rise like frozen waves, sculpted by the fierce radiation and stellar winds of the massive young stars embedded inside them. These columns are similar in nature to the famous pillars of creation inside the Eagle Nebula. Structures light years tall, dense with collapsing gas, slowly giving birth to new stars within their shadowed interiors. The name is poetic, but it is also accurate. These are genuine cradles of creation, places where gravity and gas work together in silence, building new suns that will one day shine as steadily as our own. Deep inside each pillar, shielded from the harsh light of the stars outside, protostars are quietly gathering mass, growing warmer and drifting toward the threshold of ignition. The process will continue for millions of years, long after every person alive today has been forgotten. Not every star is born alone. Many stars form in pairs, orbiting one another in systems that astronomers call binaries. Some are born in groups of 3, 4, or more, bound together by shared gravity from the very beginning. Binary stars are not unusual. It is estimated that roughly half of all stars similar to our Sun in the Milky Way belong to binary or multiple star systems. The two stars in such a pair can orbit each other closely, completing a full revolution in just days, or they can be separated by enormous distances, taking centuries or even millennia to complete a single orbit. These pairings arise naturally during the process of star formation. As a gas cloud contracts, it can fragment into 2 or more collapsing cores, each of which then ignites independently. The resulting stars remain gravitationally bound, circling one another in a long, elegant dance. From a great distance, a binary system might look like a single point of light. Only careful measurement, detecting the wobble of one star as it responds to the gravity of the other, or observing the slight dimming when one star passes in front of its companion, reveals the deeper truth. What appeared to be one light is actually 2, linked across space by the invisible thread of gravity. Stars are also born in larger groups called clusters. Open clusters are loose associations of young stars that formed together from the same parent cloud, and they can contain anywhere from a few dozen to several thousand members. These clusters drift through the galaxy as a group, still carrying traces of the nebula gas that gave rise to them. Over time, gravitational interactions with the broader galaxy gradually pull them apart, sending each star off on its own path. The Pleiades, a delicate grouping of blue-white stars, visible in the autumn and winter sky, is one of the most familiar open clusters. Its stars are roughly 100 million years old, very young by astronomical standards, and they still glow faintly through wisps of residual dust from the cloud in which they were born. The stars of the Pleiades share a common origin, having formed from the same collapsing cloud, and their compositions are strikingly similar. Siblings born from the same cosmic nursery. Over the next few 100 million years, gravitational encounters will slowly scatter them, sending each star on its own independent journey through the galaxy. Most open clusters eventually dissolve in this way, their members drifting apart until no trace of the original group remains. Our own Sun may once have been part of such a cluster, born alongside dozens or hundreds of other stars that have long since wandered away into the surrounding arms of the Milky Way. Globular clusters are something altogether different. These are ancient, densely packed spheres of stars, some containing hundreds of thousands of members held together by mutual gravity in a tight, luminous ball. Many globular clusters are more than 10 billion years old, making them among the most ancient structures in the galaxy. Their stars formed early in the history of the cosmos, when the available materials were almost entirely hydrogen and helium, with only faint traces of anything heavier. Globular clusters orbit the center of the Milky Way on long, looping trajectories, and they have survived the full sweep of galactic history, mergers, encounters, and the slow reshaping of the galaxy's structure over billions of years. To observe one through a telescope is to see a dense, shimmering globe of ancient light, a city of suns that has persisted since the universe was still young. And the sheer number of stars in the observable universe is a figure that quietly defeats the imagination. Our galaxy alone is estimated to contain somewhere between 100 billion and 400 billion stars. The Milky Way, in turn, is only one galaxy among an estimated 2 trillion in the observable universe. Multiply even the most conservative figures, and the resulting number exceeds anything the human mind can meaningfully grasp. There are more stars in the observable universe than there are grains of sand on every beach on Earth. Each one of those stars began its life in the same fundamental way, as a slow contraction within a cloud of gas, a patient gathering of matter pulled inward by gravity, a long and quiet climb toward the moment of ignition. The variety of their sizes, temperatures, colors, and lifespans is immense, but their origin is shared. Every star, from the faintest red dwarf to the most brilliant blue supergiant, was once a cold, dark wisp of hydrogen drifting through the silence of interstellar space. What makes this entire process so remarkable is not just its scale, but its patience. Star formation is not an event that happens suddenly. It is a process that unfolds across timescales that dwarf the whole of human history. The initial collapse of a gas cloud takes hundreds of thousands of years. The protostellar phase, during which the young star gathers material and contracts, can last millions of years more. And once fusion begins, the star may burn steadily for billions of years before anything changes. Compared to the lifespan of a person, or even of an entire civilization, a star is almost eternal. The sun has already shone for longer than complex life has existed on Earth, and it will continue shining long after our species has had its time. Stars do not hurry. They do not need to. They carry within them all the fuel they require, and they burn it with a patience that makes even the oldest mountains seem fleeting. Somewhere in the Milky Way, right at this very moment, a cloud of gas is pulling itself inward. It has been doing so for longer than human beings have existed as a species. Deep within its cold, dark interior, a pocket of matter is growing warmer, denser, and closer to the threshold where fusion will ignite. No telescope is watching that precise spot. No instrument has been trained on that particular patch of sky. And yet, slowly, without any urgency at all, a new star is taking shape. It will burn for longer than you can imagine, pouring light and warmth into its quiet corner of the galaxy. And when it finally fades, long after our own sun has gone dark, the atoms it forged in its core will drift outward into space and become part of something new. Another cloud, another collapse, another star. Perhaps one day another world. The universe builds itself in circles. Stars are born from the scattered remains of older stars, and they will one day return their own material to the space between them, seeding future generations with the elements they have created. It is a cycle as old as the cosmos itself, and it continues tonight, unfolding in absolute silence across distances so great that the mind grows quiet, simply trying to hold them. There is no beginning that does not carry within it the memory of something that came before, and no ending that does not quietly promise something still to come. The atoms that will build the next generation of stars are already drifting through the interstellar medium, waiting for gravity to gather them once more. And somewhere, far from any light we have yet detected, the next great cloud is already forming, vast, cold, and impossibly still, preparing itself for a collapse that will take longer than civilizations endure. Let your thoughts settle now the way starlight dims as it crosses the dark. There is nothing you need to hold on to, nothing you need to carry forward from these words. Just the gentle knowledge that somewhere in a cloud of gas older than our world, a new light is slowly beginning to glow. And the universe, as it always has, moves forward without hurry, patient, steady, and full of quiet becoming. A star, once ignited, does not simply burn. It transforms. Deep in its core, where temperatures reach millions of degrees and pressures are beyond anything the human mind can comfortably hold, the star is doing something that will shape the future of everything around it. It is building new elements, atom by atom, reaction by reaction. It is converting the simplest substance in the universe, hydrogen, into something heavier. And over the course of its lifetime, depending on how massive it is, it will continue this work, forging heavier and heavier materials in a chain of creation that stretches all the way from the lightest gas to the iron in your blood. This is the story of how stars live, how they die, and how, in doing so, they build everything that exists. The core of a star during its long, stable phase is a place of extraordinary violence, held in perfect balance. Hydrogen nuclei, bare protons, stripped of their electrons by the ferocious heat, are forced together at speeds so great that they overcome the electromagnetic repulsion that would normally keep them apart. When they collide and fuse, they form helium, and a small portion of their mass is converted into pure energy, according to the relationship that connects mass and energy at the most fundamental level of physics. That energy radiates outward through the star, pushing against the crushing weight of the layers above. And this outward pressure holds the star in a state of equilibrium, neither collapsing nor expanding, but hovering in a balance so precise it can last for billions of years. Every second, a star like our Sun converts roughly 600 million tons of hydrogen into helium. And yet the supply is so vast that the process can continue for an almost unimaginable stretch of time. The Sun has been fusing hydrogen for approximately 4.5 billion years, and still has enough remaining to continue for roughly 5 billion more. During all of that time, the star appears calm. It shines steadily. It asks for nothing. And deep inside, the quiet alchemy of fusion continues without pause. But hydrogen does not last forever. Even the most abundant fuel will eventually be consumed at the core. For a star of modest mass, one similar to our Sun, the change begins gradually. As the hydrogen in the innermost region is converted to helium, the core slowly becomes richer in helium and poorer in hydrogen. Fusion does not stop immediately, but it shifts. A shell of hydrogen surrounding the now helium-rich core continues to burn. and the energy produced by that shell actually increases. The additional energy pushes the star's outer layers outward. The surface expands, and as it does, it cools, not because the star is losing energy, but because that energy is now being spread across a vastly larger surface area. A star that once glowed a steady yellow-white begins to take on a warm, deep orange and eventually a rich red. It has become a red giant. This transformation is immense in scale. When our own sun reaches this phase, billions of years from now, its outer edge will swell to roughly the orbit of the Earth. The inner planets, Mercury, Venus, and likely Earth itself, will be engulfed by the expanding envelope of gas. The sun that once warmed our world from a comfortable distance will become a vast, diffuse sphere of cooling light, hundreds of times its current diameter. It will look nothing like the star we know. And yet inside, the process of element building will have taken a new and important step. As the core contracts and heats up further, reaching temperatures of roughly 100 million degrees, helium itself begins to fuse. 3 helium nuclei combine to form a single nucleus of carbon, and in some cases, a 4th helium nucleus is captured to produce oxygen. These reactions are more difficult than hydrogen fusion, requiring higher temperatures and greater pressures, but they proceed nonetheless. For the first time, the star is producing elements that will one day become essential to life. Carbon and oxygen, the 2 atoms that form the backbone of every living molecule on Earth, are being forged in the heart of an aging star. For a star roughly the mass of our sun, the story does not go much further than this. Carbon and oxygen accumulate in the core, but the temperature and pressure never rise high enough to ignite the next stage of fusion. The star has reached its creative limit. What happens next is one of the most gentle and beautiful endings in all of nature. The outer layers of the red giant, no longer held tightly by the weakening grip of gravity, begin to drift away. They do not explode. They are not torn apart. They simply lift off, slowly and gracefully, like mist rising from a still pond. Over tens of thousands of years, these layers expand outward into space, forming a glowing shell of gas, illuminated from within by the hot, exposed core of the star. This shell is called a planetary nebula, a misleading name, since it has nothing whatsoever to do with planets. Early astronomers gave it that label because, through small telescopes, some of these nebulae appeared as round, greenish disks that vaguely resembled distant worlds. The name has persisted, even though we now understand exactly what they are. They are the final breath of a dying star, a slow and luminous release of material back into the universe. And at the center of that expanding shell, all that remains of the star itself is its exposed core. A dense, hot sphere of carbon and oxygen, roughly the size of the Earth, but containing a mass comparable to that of the Sun. This object is called a white dwarf. It no longer generates energy through fusion. It shines only because it is still radiating the leftover heat from its former life. Over billions of years, it will slowly cool, growing dimmer and dimmer, fading from white to yellow, to orange to red, and eventually, in theory, to a cold, dark remnant that emits no light at all. No white dwarf in the universe has yet reached that final state, because the cooling process takes longer than the current age of the cosmos. Every white dwarf that has ever formed is still glowing somewhere, still releasing the heat of its past, still slowly winding down. It is an ending that stretches across an almost eternal span, patient, unhurried, and profoundly quiet. But for stars far more massive than our Sun, the story takes a dramatically different path. A star with 8 or 10 or 20 times the mass of the Sun does not stop at carbon and oxygen. The gravitational pressure in its core is so much greater that it can ignite each successive stage of fusion that a smaller star cannot reach. After hydrogen is exhausted and helium begins to fuse, the core contracts further and grows hotter still. Carbon ignites, producing neon and magnesium. Then neon itself is consumed, producing more oxygen. Then oxygen fuses, creating silicon and sulfur. And finally, silicon fuses into iron. Each stage requires higher temperatures and greater pressures, and each stage lasts for a shorter period than the one before it. Hydrogen burning may sustain a massive star for millions of years. Helium burning lasts for perhaps hundreds of thousands. Carbon burning may endure for only a few thousand years. Oxygen burning lasts months. Silicon burning, the final stage, is over in roughly a single day. The star has become a series of nested shells, each one fusing a different element, layered like the rings of an onion around a core that is growing denser and heavier with each passing hour. And then it reaches iron, and everything changes. Iron is the end point of stellar fusion, and the reason is rooted in the deepest principles of nuclear physics. Every fusion reaction that preceded this one, hydrogen to helium, helium to carbon, carbon to neon, and so on, released energy. The products of each reaction weighed slightly less than the ingredients, and that tiny difference in mass was converted into the energy that powered the star. But iron is different. Iron has the most tightly bound nucleus of any element. To fuse iron into anything heavier would not release energy. It would require energy, absorbing it from the star's surroundings, rather than contributing to the outward pressure that holds the star up. For the first time in a star's life, the engine at its heart has no more fuel it can profitably burn. Fusion does not just slow down, it stops providing the support the star depends on. The core, now composed almost entirely of iron, is suddenly left without the outward pressure that has balanced gravity for millions of years. And gravity, which has been waiting all this time, presses in with overwhelming force. What follows happens in less than a second. The iron core collapses inward at a significant fraction of the speed of light. Electrons are forced into protons, creating neutrons and releasing a flood of ghostly particles called neutrinos. The core compresses until the neutrons themselves are packed so tightly that they resist further compression. A sudden, immovable wall of nuclear matter. The infalling outer layers of the star slam into this wall and rebound outward in a shock wave of almost unimaginable energy. The star explodes. This is a supernova, one of the most powerful events in the known universe. For a brief period, a single exploding star can outshine an entire galaxy, pouring out more energy in a few weeks than our Sun will produce over its entire lifetime. The light from a supernova can be visible in the daytime sky, and historical records from cultures around the world describe sudden new stars appearing where none had been before, blazing for weeks or months before slowly fading away. But the importance of a supernova is not its brightness, it is what it scatters. When the outer layers of the star are hurled outward, They carry with them every element the star forged during its lifetime: carbon, oxygen, nitrogen, silicon, sulfur, calcium, and iron. And in the incredible heat and pressure of the explosion itself, something additional happens. Elements heavier than iron, which the star could not create through ordinary fusion, are produced in the chaos of the blast. Neutrons, released in enormous numbers during the collapse, are captured by existing nuclei at a furious rate, building heavier and heavier atoms in fractions of a second. Cobalt, nickel, copper, zinc, silver, gold, and even lead, the heaviest stable elements in the periodic table, are forged in the fires of a dying star. These atoms, newly made in the final moments of the explosion, are flung outward along with everything else, spreading across light years of space and mixing with the surrounding interstellar medium. A supernova does not merely end a star's life. It distributes the product of that life across the galaxy, seeding the clouds of gas and dust from which future stars and future planets will one day form. This is one of the most profound ideas in all of science. Every atom of carbon in your body was made inside a star. Every atom of oxygen you breathe was forged in a stellar core. The calcium in your bones, the iron in your blood, the phosphorus in your DNA. All of it was produced by nuclear fusion inside stars that lived and died long before our solar system existed. You are not merely looking at the stars when you gaze at the sky. You are looking at the forges that built you. The connection between your body and the interior of a distant, ancient sun is not metaphorical. It is literal. It is chemistry. It is physics. And it is one of the most quietly astonishing truths about the nature of existence. But supernovae are not the only forges that create the heaviest elements. There's a second kind of cosmic event, rarer and in some ways even more extraordinary, that contributes many of the atoms we find on Earth today. When two neutron stars, those incredibly dense remnants left behind by earlier supernovae, happen to orbit each other, they do not do so forever. Over millions or even billions of years, they spiral slowly inward, drawn closer by the gradual loss of energy through gravitational waves, subtle ripples in the fabric of space and time itself. The spiral is patient beyond measure. Two neutron stars born from separate supernovae in the same binary system might circle each other for longer than our sun has existed, drawing imperceptibly closer with each orbit. The distance between them shrinks by fractions so small that no human instrument could detect the change from one year to the next. And yet, over sufficient time, the gap closes. The orbits tighten. The speed increases. And in the final moments, the last few seconds of a journey that may have lasted billions of years, the two objects collide and merge in an event called a kilonova. A kilonova is brief and violent, but its consequences ripple outward for light years. When two neutron stars merge, the collision produces temperatures and densities that rival or exceed those of even the most powerful supernovae. In that extreme environment, neutrons are liberated in staggering quantities, and they are captured by atomic nuclei so rapidly that the heaviest elements in the periodic table are assembled in abundance. Gold, platinum, uranium, and many of the rare earth elements that are scarce on our planet are produced in these mergers in quantities that dwarf what a single supernova can create. Astronomers confirmed this in 2017, when gravitational wave detectors recorded the signal of two neutron stars colliding in a galaxy roughly 130 million light-years away. Telescopes around the world observed the afterglow, and the light carried the unmistakable spectral signatures of newly forged heavy elements, freshly made atoms glowing in the debris of the merger. It was the first direct observation of heavy element production outside of a supernova, and it revealed that much of the gold and platinum on Earth may have originated not in the explosion of a single massive star, but in the slow, spiraling death dance of two stellar corpses, finally meeting after an unimaginably long courtship. There is something hauntingly beautiful about this. Two stars live, burn through their fuel, and die in separate explosions. Their collapsed cores, neutron stars, each one smaller than a city yet heavier than our sun, are flung into orbits around each other by the violence of those deaths. And then, across billions of years of silent spiraling, they find each other again and merge, creating in that final instant the very atoms that will one day become part of a wedding ring, or a circuit board, or the trace elements in a living cell. The gold in the Earth's crust may carry within it the memory of two dead stars that spent longer than the age of our solar system falling toward one another as the dark. When the expanding shell of a supernova or the scattered debris of a kilonova drifts outward into space, it forms a vast, ragged cloud of enriched gas and dust that can persist for tens of thousands of years. These remnants glow in many wavelengths, their filaments of hot gas shining in X-rays, visible light, and radio waves. Over time, they mix with the surrounding interstellar medium, stirring in their cargo of heavy elements. But that mixing is not instantaneous. It is a process as slow and patient as everything else in the story of stars. The enriched material drifts outward at speeds that seem enormous by human standards, thousands of kilometers per second in the earliest phase. But that gradually slow as the remnant collides with the thin gas already present between the stars. Over tens of thousands of years, the expanding shell sweeps up more and more interstellar material, like a wave gathering sand. It cools as it spreads. Its glow fades. And eventually, the remnant merges so completely with the surrounding medium that it can no longer be distinguished as a separate structure. The atoms it carried, the carbon, the oxygen, the iron, the gold, become part of the general background of interstellar gas, drifting anonymously through the galaxy. This enriched gas does not simply sit still. It moves, carried by the slow currents that flow through the interstellar medium. Currents driven by the combined effects of stellar winds, radiation pressure, supernova shock waves, and the rotation of the galaxy itself. Over millions of years, enriched gas from one region of the galaxy can migrate to another, mixing with gas from entirely different stellar sources. Streams of material from dozens or hundreds of separate supernovae and kilonovae blend together, creating a cocktail of elements whose composition reflects the accumulated contributions of countless stellar lifetimes. By the time this gas finds its way into a new collapsing cloud, one that will eventually give rise to a new generation of stars, it carries a chemical history so rich and so layered that no single star can claim credit for its contents. The cloud from which our own solar system formed was exactly such a mixture, a blend of primordial hydrogen and helium with heavier elements contributed by stars that had lived and died across billions of years and across thousands of light years of galactic space. When a patch of this enriched gas becomes dense enough to begin collapsing under its own gravity, the same process we followed at the very beginning of this journey. The heavier elements it carries play a crucial role in what comes next. Dust grains made of silicon, carbon, iron, and other heavy atoms help the collapsing cloud cool more efficiently by radiating away heat. That cooling allows the gas to contract more readily, forming denser cores that will eventually become protostars. As the protostar grows and its accretion disk takes shape, the heavier elements within that disk begin to stick together, forming tiny solid particles that collide, merge, and gradually build into larger and larger objects, pebbles, boulders, and eventually the rocky bodies that will become planets. Without the heavy elements scattered by earlier generations of stars, there would be no dust, no rocky cores, no solid worlds. Gas giants might still form, but the small, dense, warm planets like Earth, the kind that can hold liquid water and sustain complex chemistry, depend entirely on the inheritance passed down from dead suns. Our own sun is thought to be a third-generation star, perhaps even later, meaning that the cloud from which it formed had already been enriched by multiple rounds of stellar life and death. The iron in the core of the Earth, the oxygen in our oceans, the silicon in our rocks, all of it passed through at least one star before arriving here. Some of it may have passed through several. And what of the core left behind after the explosion? In the most massive supernova, the remnant core is crushed beyond the point of anything we encounter in ordinary experience. The neutrons, packed together under unimaginable pressure, form an object called a neutron star, a sphere perhaps only 20 kilometers across, yet containing more mass than our entire sun. A single teaspoon of neutron star material would weigh roughly 1 billion tons. The density is almost beyond comprehension. The surface gravity is so intense that a human standing on it, were such a thing conceivable, would be crushed to a film of atoms thinner than paper. Some neutron stars rotate at extraordinary speeds, spinning dozens or even hundreds of times per second, sweeping beams of radiation across the sky like cosmic lighthouses. These are called pulsars, and their regular, repeating signals were so precise when first discovered that astronomers briefly wondered whether they might be artificial, signals from an intelligent civilization somewhere in the galaxy. They are not, of course. They are the spinning remnants of dead stars, broadcasting their presence into the void with a regularity that rivals the finest clocks ever built. Not every massive star leaves behind a neutron star. For the most massive of all, those whose cores exceed a certain critical mass even after the explosion, the collapse continues past the neutron star phase entirely. But that story lies a little further along this journey. And for now, it is enough to know that the most extreme stars in the universe meet the most extreme endings. What matters here, in this moment, is the cycle. Stars are born from clouds of gas. They burn for millions or billions of years, fusing lighter elements into heavier ones. When they die, whether gently as white dwarfs surrounded by glowing planetary nebulae, or violently as supernovae scattering their contents across light years of space, or in the rare and spectacular collision of neutron stars merging long after their parent stars have gone, they return their material to the universe. That material mixes with the interstellar medium, enriching it, adding complexity, adding possibility. And from those enriched clouds, new stars form, carrying within them the inheritance of everything that came before. This cycle has been repeating for more than 13 billion years. The very first stars in the universe, born from the pristine hydrogen and helium produced in the earliest moments after the Big Bang, contained no heavy elements at all. They were enormous, brilliant, and short-lived, burning through their fuel in just a few million years before exploding and scattering the first carbon, the first oxygen, the first iron into the young cosmos. Those elements became part of the next generation of stars, which lived and died in turn, adding still more complexity to the mix. Generation after generation, the universe grew richer. The periodic table filled in, element by element, each one the product of a star that once shone and then was gone. By the time our own sun formed, roughly 4.5 billion years ago, the raw materials available included everything needed to build a rocky planet with liquid water, a breathable atmosphere, and eventually living things capable of looking up and wondering where they came from. The answer, as it turns out, is everywhere. You came from the interstellar medium. You came from the cores of ancient stars. You came from supernova explosions that scattered their elements across the galaxy long before the Earth existed. And you came, in part, from the collision of neutron stars that spiraled together across billions of years and merged in a flash that seeded the cosmos with its rarest materials. The carbon in your muscles was once part of a stellar core burning at 100 million degrees. The oxygen filling your lungs was fused from helium in the heart of a red giant. The iron carrying oxygen through your bloodstream was the very last element a massive star produced before its core collapsed, and its outer layers were flung into the dark. The gold in trace amounts within your body may have been forged when two neutron stars collided in a distant part of the galaxy, long before our corner of space had even begun to take shape. Even the rarer elements, the traces of copper and zinc in your cells, the tiny amounts of cobalt and molybdenum that your body requires to function, were built in the extreme conditions of supernovae and kilonovae, forged in seconds and scattered across distances so vast that millions of years passed before they came to rest in the cloud that would become our solar system. There is a way of thinking about nebulae that shifts once you understand this cycle. Earlier in this journey, we visited nebulae as nurseries, places where new stars are born from collapsing clouds of gas and dust. That is true, and it remains true. But nebulae are also graveyard. The planetary nebulae left behind by dying sun-like stars are the shed skins of stellar old age, expanding shells of carbon and oxygen drifting outward into the void. The supernova remnants left behind by massive stars are the scattered remains of violent deaths, laced with every element the star ever created. These two kinds of nebulae, one gentle, one fierce, both serve the same ultimate purpose. They return material to the interstellar medium. They replenish the supply of gas and dust from which new stars will form. In doing so, they close the loop. Death feeds birth. Endings become beginnings. The universe does not waste anything. Every atom that was once part of a star will, given enough time, become part of another star, or a planet, or a moon, or a grain of dust drifting through the cold between worlds. Nothing is lost. Everything is recycled. The cosmos is, in the deepest and most literal sense, a system of endless reuse. And what strikes you, when you sit with this idea for a while, is how quiet the whole process is. Stars do not announce their births. They do not cry out when they die. The fusion that builds carbon from helium occurs in absolute silence, in a vacuum where no sound could ever carry. The supernova that scatters iron and gold across 100 light years produces no thunder, no roar, no sound of any kind. The planetary nebula that drifts outward from a dying white dwarf does so without a whisper. All of it, every stage of stellar life, every phase of creation and destruction, every act of elemental alchemy, happens in the deepest silence imaginable. The universe builds its most magnificent structures, creates its most essential materials, and distributes the ingredients for life itself across billions of light years. And it does all of it without making a single sound. This silence is not emptiness. It is not absence. It is the natural condition of a cosmos where matter and energy interact through gravity and electromagnetism and nuclear forces, but never through the vibrations of air that our ears are designed to detect. Sound requires a medium, molecules packed closely enough together to transmit pressure waves, and space does not provide one. The interstellar medium is far too thin. The voids between stars are far too vast. And so the grandest processes in nature proceed in a hush so complete that even the word silence feels insufficient to describe it. Think about that for a moment. Every star you have ever seen in a night sky is burning in perfect quiet. The nebulae, glowing softly in the arms of the Milky Way, are silent. The supernova remnants, still expanding outward thousands of years after the explosion that created them, carry no sound with them. The neutron stars, spinning hundreds of times per second, do so without the faintest hum. The entire visible universe, with its hundreds of billions of galaxies, each containing hundreds of billions of stars, unfolds in a stillness so profound that it becomes, in its own way, a kind of peace. And within that peace, the work of creation goes on. Right now, somewhere in the galaxy, a massive star is fusing silicon into iron in its core. It has only hours left. When it collapses, the elements it has spent millions of years building will be released into the cosmos, joining the vast reservoir of material from which future worlds will be assembled. Some of those atoms may one day become part of a planet. Some may become part of an ocean, or a mountain, or a living cell. The star does not know this. It cannot know this. It simply burns and fuses, and when the time comes, it lets go of everything it has made. There is something restful in that idea, that the universe does not cling to what it creates, that every star gives back what it was given, enriched and transformed by the life it lived, that the atoms in your body are on loan from the cosmos, borrowed for a brief moment of warmth and awareness before they return to the great slow cycle of stellar birth and death. You are not separate from this process. You are part of it. You always have been. And when you breathe out tonight, the carbon in your breath will begin its own long journey, drifting, mixing, waiting to become part of something new. Perhaps another cloud, perhaps another star, perhaps in some distant future, another quiet evening on a world not yet imagined, where someone rests beneath unfamiliar constellations and wonders, as you do now, where they came from. The answer will be the same. They came from the stars, as did you, as did everything. Let that thought carry you gently forward. There is more of this story to tell, about the places where gravity reaches its most extreme, about the vast distances between things, and about the age of everything. But for now, let these ideas settle like dust drifting through starlight. The elements that make you are ancient beyond measure, and they will endure long after this night has passed. You are, in the most peaceful and literal sense, a small piece of the universe, resting quietly within itself. At the end of a massive star's life, when the iron core has collapsed and the outer layers have been flung outward in a supernova, something remains behind. In many cases, that remnant is a neutron star, a dense, spinning sphere of compressed matter only a few kilometers across. But for the most massive stars of all, even this is not the final state. If the collapsing core exceeds a certain critical mass, roughly 3 times the mass of our Sun, then no known force in the universe can halt the collapse. Not the pressure of electrons, not the resistance of neutrons packed shoulder to shoulder. Nothing. Gravity, patient and absolute, overwhelms everything else, and the core continues to contract past every boundary that physics can describe with certainty. What remains is a region of space where gravity has become so extreme that nothing, not light, not matter, not information of any kind, can escape from within it. This is a black hole. And despite everything you may have heard about them, they are not monsters. They are not cosmic vacuum cleaners pulling everything toward them with an irresistible and terrifying force. They are, in the most precise sense, simply places where gravity has won, completely, quietly, and without any possibility of reversal. The first thing to understand about a black hole is what it is not. A black hole does not reach out across space and drag things in. At any given distance, the gravitational pull of a black hole is exactly the same as the gravitational pull of any other object with the same mass. If our Sun were somehow replaced by a black hole of identical mass, without the explosion, without the disruption, purely as a thought experiment, the planets would continue orbiting exactly as they do now. Their paths would not change. They would not spiral inward. They would not be swallowed. The gravity at the distance of the Earth's orbit would be precisely the same, because gravity depends on mass and distance, not on the nature of the object producing it. What makes a black hole different is not the strength of its gravity at a distance, but the fact that its mass is compressed into such a small region that you can get extraordinarily close to all of it. And when you get close enough, closer than you could ever approach the surface of a normal star, because a normal star has a physical surface that stops you, gravity becomes so intense that the rules of ordinary experience break down entirely. The boundary beyond which nothing can return is called the event horizon. It is not a physical surface. There is no wall, no barrier, no edge you could touch or see. It is a mathematical boundary, a sphere defined by the point at which the escape velocity equals the speed of light. Anything that crosses inward past this boundary, light, matter, radiation, is captured, not because it is pulled with sudden violence, but because the geometry of space and time has curved so deeply that every possible path leads further inward. An object falling through the event horizon would not feel a dramatic jolt. If the black hole were large enough, the crossing might even feel uneventful in the moment. But once past that line, return becomes impossible. The future, in a very real physical sense, points only inward. What lies at the center of a black hole is something that current physics cannot describe with confidence. The mathematics of general relativity, the framework that describes gravity as the curvature of space and time, predicts that the collapsing matter continues inward until it reaches a point of infinite density called a singularity. But physicists are cautious about this prediction, because infinite density is not a physical description so much as a signal that the theory has reached its limit. When a mathematical model produces an infinity, it usually means the model is incomplete, not that nature has actually created something infinite. At the heart of a black hole, the conditions are so extreme that general relativity and quantum mechanics, the two great pillars of modern physics, would need to be unified in order to give a reliable answer. That unification has not yet been achieved. And so the interior of a black hole remains, for now, one of the deepest open questions in all of science. We know what happens outside the event horizon. We can observe it, model it, and test our predictions. But what happens inside is, by definition, hidden from us. The event horizon is not merely a barrier to escape. It is a barrier to knowledge. This means that when we say we have observed a black hole, we must be precise about what we mean. No one has ever seen a black hole directly. What we observe are the effects that a black hole produces on the space and matter around it. And those effects can be spectacular. When gas and dust fall toward a black hole, drawn inward by gravity, often from a companion star or from the surrounding interstellar medium, they do not fall in a straight line. Instead, the material spirals inward, forming a vast, flattened disk of swirling matter called an accretion disk. As the gas in this disk orbits faster and faster, drawing closer to the event horizon, friction between the particles heats the material to extraordinary temperatures, millions of degrees in some cases. At those temperatures, the gas glows with intense radiation, emitting X-rays and other high-energy light that can be detected by telescopes in orbit around the Earth. This glow does not come from the black hole itself. It comes from the material being compressed and heated just outside the point of no return. The black hole remains dark, but the infalling matter announces its presence with a brilliance that can outshine entire galaxies. Gravitational lensing provides another way to detect the presence of a black hole, even when there is no accretion disk to betray it, because a black hole warps the geometry of space around it. Light passing nearby follows curved paths rather than straight ones. This means that a black hole can bend, distort, and magnify the light from objects behind it, producing strange visual effects, arcs, rings, and duplicated images of background stars or galaxies. Even a black hole sitting in otherwise empty space would leave a gravitational fingerprint, subtly bending the light of everything beyond it. This effect is not unique to black holes. Any massive object curves space and bends light to some degree. But the extreme compactness of a black hole makes its lensing particularly dramatic. In some cases, the warped light forms a bright ring around the black hole's shadow, outlining the region from which no light escapes. This is what was captured in the historic images produced by a global network of radio telescopes, which revealed the glowing ring of superheated gas surrounding the supermassive black hole at the center of the galaxy, known as M87. The dark shadow at the center of that image is not the black hole itself. It is the absence of light, the region where the event horizon prevents anything from reaching our instruments. We see the glow around it, and we see the shadow it casts, but the black hole itself remains hidden, defined only by what it does not allow us to see. Supermassive black holes are a different kind of object entirely from the stellar mass black holes left behind by individual dying stars. While a stellar black hole might contain 5, 10, or perhaps 50 times the mass of our Sun, a supermassive black hole can contain millions or even billions of solar masses. These colossal objects sit at the centers of most large galaxies, including our own Milky Way. The supermassive black hole at the center of our galaxy is called Sagittarius A star, and it contains roughly 4 million times the mass of our Sun. Despite its enormous mass, it is relatively quiet at the moment. It is not actively consuming large amounts of material, and its accretion disk is faint compared to the blazing cores of more active galaxies. We know it is there because astronomers have tracked the orbits of individual stars near the center of the galaxy for decades. Those stars move at tremendous speeds, tracing tight elliptical paths around an invisible point of overwhelming gravity. By measuring their orbits with extraordinary precision, scientists have calculated the mass of the unseen object and confirmed that it can only be a black hole. Nothing else with that much mass confined to that small a region is consistent with the laws of physics as we understand them. In other galaxies, supermassive black holes can be far more active. When large quantities of gas fall inward and form a thick, luminous accretion disk, the resulting outpouring of energy can turn the galaxy's core into one of the brightest objects in the observable universe. These active galactic nuclei, at their most extreme, are known as quasars, objects so luminous they can be detected across billions of light years, their light outshining the combined glow of every star in their host galaxy. Quasars were among the first clues that supermassive black holes existed at all. When astronomers first detected them in the early 1960s, their extraordinary brightness and great distances were deeply puzzling. No known process involving stars could produce so much light from so compact a region. Only later did it become clear that the energy source was gravitational, matter falling toward a black hole, converting its motion into radiation with a remarkable efficiency that exceeds even nuclear fusion. A quasar is not the black hole itself shining. It is the last cry of matter before it crosses the event horizon. A final blaze of light from material that is about to disappear forever. How supermassive black holes form in the first place is still an open question. They are present in the centers of galaxies that are already very old, which means they must have grown to enormous sizes relatively quickly in cosmic terms. Some may have begun as stellar mass black holes left behind by the first generation of massive stars, and then grown over billions of years by consuming gas and merging with other black holes. Others may have formed through the direct collapse of vast clouds of gas in the early universe, bypassing the stellar stage entirely and creating an intermediate mass seed that then continued to grow. The truth likely involves more than one pathway, and astronomers continue to study the earliest galaxies for clues about how these giants came to be. What is clear is that supermassive black holes are not rare anomalies. They appear to be a standard feature of large galaxies, as fundamental to galactic structure as the stars and gas that surround them. The relationship between a galaxy and its central black hole is one of the deepest and least fully understood connections in modern astrophysics. When you step back from the individual objects and look at the universe on its largest scales, a new kind of structure emerges, one that has nothing to do with individual stars or even individual galaxies, but with the way matter is distributed across the observable cosmos. Galaxies are not scattered randomly through space. They are organized. They gather along enormous filaments and sheets that stretch across hundreds of millions of light years, forming a vast interconnected network that astronomers call the cosmic web. Between these filaments lie great voids, immense regions of space where galaxies are rare or absent, stretching for tens of millions of light years in every direction. The cosmic web is the largest known structure in the universe, and its shape was determined not by chance, but by the very earliest moments of cosmic history. In the first fraction of a second after the Big Bang, the universe was almost perfectly smooth, but not quite. Tiny fluctuations in density, variations so small they amounted to only parts in 100,000, were imprinted across the fabric of space. As the universe expanded and cooled, gravity amplified these fluctuations. Regions that were ever so slightly denser than average pulled in a little more matter. Over hundreds of millions of years, those modest overdensities grew into the nodes and filaments of the cosmic web. Galaxies formed along the densest filaments, clustering together at the intersections where multiple strands of the web converge. The voids between them emptied out as matter flowed toward the denser regions. The result, after billions of years of quiet gravitational sculpting, is the web-like structure that galaxy surveys reveal today. A pattern that looks, in three-dimensional maps, like an intricate lattice of glowing threads separated by vast, dark bubbles. What makes this structure even more remarkable is that most of the mass responsible for shaping it is invisible. Ordinary matter, the atoms that make up stars, planets, gas, and dust, accounts for only about 5% of the total mass-energy content of the universe. Roughly 27% is something called dark matter, a substance that does not emit, absorb, or reflect light in any wavelength, and that interacts with ordinary matter only through gravity. We cannot see dark matter. We cannot detect it directly with any current instrument. But we know it is there because its gravitational influence is written across the cosmos. The evidence comes from multiple independent sources. Galaxies rotate too quickly for their visible mass to hold them together. The outer stars orbit so fast that they should fly away if only the visible matter were providing gravity. But they do not fly away. Something unseen is holding them in place. Galaxy clusters, too, contain far more gravitational mass than their visible components can account for. The hot gas between cluster galaxies moves at speeds that imply a gravitational well much deeper than the galaxies themselves could create. And gravitational lensing, the bending of light around massive objects, consistently reveals more mass than can be seen. When astronomers model the distribution of matter needed to produce the observed lensing effects, they find that the majority of it is dark. The luminous galaxies, are like bright beads scattered along threads of invisible structure. The threads themselves, the scaffolding of the cosmic web, are made primarily of dark matter. Dark matter halos surround individual galaxies, extending far beyond the visible stars. Our own Milky Way sits inside such a halo, a vast, roughly spherical cloud of dark matter that extends hundreds of thousands of light years from the galactic center, far beyond the outermost stars. This halo shaped the galaxy's formation. It was the gravitational well of the dark matter that first gathered the ordinary gas inward, allowing it to cool, condense, and form the disk of stars we see today. Without dark matter, the Milky Way as we know it might not exist. The stars and gas are the visible inhabitants, but the dark matter is the architecture, the invisible framework on which the visible universe was built. And then there is something stranger still. The remaining 68% of the universe's mass energy content is attributed to something called dark energy, a mysterious property of space itself that appears to be driving the accelerating expansion of the universe. Dark energy does not clump. It does not form structures. It does not interact with matter in any way that we can directly measure. Its presence is inferred entirely from the observation that the expansion of the universe is not slowing down, as gravity alone would predict, but speeding up. Distant galaxies are receding from us at rates that increase with distance, and the rate of that recession is itself increasing over time. Something is pushing the universe apart, and that something accounts for the majority of all that exists. We do not know what dark energy is. We do not know whether it will remain constant or change over time. We know only that it is there, written into the behavior of the cosmos on the grandest scales imaginable, and that without it, the universe we observe would not look the way it does. Together, ordinary matter, dark matter, and dark energy compose the full inventory of the cosmos. The fraction that we can see, the stars, the gas, the dust, the planets, everything that shines or reflects or emits, is a tiny minority. The universe is mostly dark, mostly invisible, mostly made of things we have not yet fully understood. This is not a failure of science. It is one of its most honest and remarkable admissions. We have mapped the visible universe with extraordinary precision. We have identified the forces that shaped its large-scale structure. We have traced the cosmic web across billions of light years and counted galaxies by the hundreds of billions. And in doing all of this, we have discovered that the universe is vastly larger and stranger than its visible components alone would suggest. What we can see is the surface of something much deeper. The cosmic web stretches across the entire observable universe, and its scale is almost impossible to hold in the mind. The observable universe, the region from which light has had time to reach us since the Big Bang, spans roughly 93 billion light years in diameter. Within that volume, there are an estimated 2 trillion galaxies, each one containing billions or hundreds of billions of stars. The filaments of the cosmic web connect these galaxies across distances of hundreds of millions of light years, and the voids between filaments can stretch even farther. The sheer quantity of space involved is numbing. Light, traveling at 300,000 kilometers per second, would need billions of years to cross from one side of the observable universe to the other. And the observable universe is not the whole universe. It is merely the portion we can see. The sphere defined by the distance light has been able to travel since the cosmos began. Beyond that boundary, there is almost certainly more universe, more galaxies, more stars, more structure. But their light has not yet had time to reach us, and it may never reach us, because the expansion of space is carrying those regions away faster than their light can close the gap. This is one of the most quietly staggering implications of modern cosmology. There are regions of the universe that we will never be able to observe, no matter how long we wait or how powerful our instruments become. The expansion of space is not the motion of galaxies through a fixed background. It is the stretching of space itself, and on the largest scales, that stretching can carry distant regions away from us at an effective rate that exceeds the speed of light. This does not violate any law of physics, because the speed limit imposed by relativity applies to objects moving through space, not to the expansion of space itself. The result is a cosmic horizon, a boundary beyond which the universe is forever out of reach. What lies beyond it is not nothing. It is simply unknown, and by the nature of the expansion, it will remain so. We are surrounded by a universe that extends further than we will ever see. A thought that is both humbling and, in its own way, peaceful. Within the observable universe, the large-scale structure carries a remarkable uniformity. On the grandest scales, spanning billions of light years, the distribution of matter looks roughly the same in every direction. This is known as the cosmological principle, the observation that the universe, viewed on the largest scales, has no preferred center and no preferred direction. Every point in the cosmos sees roughly the same pattern of galaxies, filaments, and voids. This uniformity is a legacy of the early universe, when matter was distributed almost, but not quite, evenly. The tiny fluctuations that existed then have grown into the structures we see today, but the overall texture remains consistent. The universe is lumpy on small scales. Galaxies cluster, filaments connect, voids empty, but smooth on the largest scales, like a fabric that appears textured up close but uniform from a great distance. And through all of this, the black holes, the cosmic web, the dark matter scaffolding, the accelerating expansion, there is a thread of quiet that holds the story together. Black holes, despite their reputation, are among the quietest objects in the universe. A solitary black hole, sitting in empty space, does nothing at all. It exerts gravity, as any mass does, but it emits no light, produces no sound, and interacts with nothing unless something happens to fall close enough to notice. It simply exists, a region of curved space, a remnant of a star that once shone, now dark and still. Even the most active black holes, those surrounded by blazing accretion disks and powerful jets of matter, are silent. The jets produce radiation, not sound. The accretion disk glows, but it does not roar. In the vacuum of space, all of this fury unfolds without a whisper. The cosmic web itself is silent. The filaments of dark matter that connect galaxy clusters stretch across distances so vast that light needs hundreds of millions of years to traverse them. And they do so without producing any vibration that a human ear could detect. Galaxies drift along these filaments, drawn by gravity, moving at hundreds of kilometers per second relative to one another, and yet the space between them carries no sound. The voids are silent. the clusters are silent. The entire architecture of the observable universe, the grandest structure that exists, operates in a quiet so deep and so total that it redefines what silence means. There is something restful in this. The universe, for all its vastness and complexity, is not loud. It is not chaotic in the way we sometimes imagine. The processes that shape it, gravity, fusion, expansion, are powerful beyond measure, but they work without noise. Stars burn in silence. Black holes consume in silence. The cosmic web grows and stretches in silence. And the dark matter that holds everything together does so without ever being seen or heard. The universe is, at its deepest level, a place of extraordinary stillness, not the stillness of emptiness, but the stillness of immense processes unfolding on timescales so long and across distances so great that they produce a kind of peace simply by being too vast for anything as small as sound to carry. If you were drifting in the space between galaxies right now, far from any star, far from any world, you would experience the most complete silence that exists anywhere in nature. No wind, no vibration, no sound of any kind, only the faint, ancient glow of the cosmic microwave background, the remnant radiation from the earliest era of the universe, arriving from every direction at once, too faint and too far below the threshold of your senses to perceive. And in that silence, the universe would continue its work. Stars would be born, stars would die, black holes would grow, one atom at a time. The cosmic web would stretch a little further, and the expansion of space would carry the farthest galaxies a little farther beyond your reach, gently and without any sound at all. Let the scale of it settle into you like a slow breath. You do not need to hold it. You do not need to understand every detail. It is enough to know that you are part of this. A small, warm, conscious arrangement of atoms resting on a rocky world that circles an ordinary star, which orbits the center of a galaxy held together by invisible matter, which drifts along a filament of the cosmic web, which stretches across a universe so vast and so quiet that the very idea of it invites you to let go, to soften, and to simply rest within the immensity of all that is. There is a unit of measurement in astronomy that sounds simple when you first hear it, but becomes more extraordinary the longer you sit with it. A light year. It is not a measure of time, though the word year is right there inside it. It is a measure of distance, the distance that light travels in 1 year. Light moves at roughly 300,000 kilometers per second. In a single second, it could circle the Earth more than 7 times. In 1 minute, it crosses more than 18 million kilometers. In 1 hour, it travels more than 1 billion kilometers. And in 1 year, moving at that speed without pause, without slowing, it covers approximately 9.5 trillion kilometers. That is 1 light year. It is a distance so vast that writing it out in ordinary numbers becomes almost meaningless. The figures are simply too large for the mind to hold in any useful way. And yet, when astronomers describe the distances between stars, they use light years the way you might use city blocks, casually, as a matter of routine, because in the context of the universe, even this enormous unit feels modest. The nearest star to our own sun is Proxima Centauri, a small, faint red dwarf sitting just over 4 light years away. That means the light you would see from Proxima Centauri tonight, if your eyes were sharp enough to catch it, which they are not because it is far too dim, left that star more than 4 years ago. You would be seeing it not as it is now, but as it was when that light began its journey. 4 years is a short delay by cosmic standards. It is barely worth mentioning when set against the deeper distances of the galaxy. And yet, consider what that distance actually means in human terms. The fastest spacecraft ever launched from Earth, the Voyager probes, travel at roughly 17 kilometers per second. At that speed, it would take more than 70,000 years to reach Proxima Centauri. 70,000 years. That is longer than the entirety of recorded human history, longer than the existence of agriculture, longer than the age of every city, every empire, every written language. The nearest star is, by any practical human measure, unreachably far away. And it is the closest one. Everything else is farther. The stars that are visible to the naked eye on a clear night span a range of distances, but most of them lie within a few hundred to a few thousand light years of Earth. That sounds like a large volume of space, and it is, but it represents only a tiny sliver of the Milky Way. Our galaxy is a vast, rotating disk of stars, gas, and dust stretching roughly 100,000 light years from one edge to the other. The Sun sits about 26,000 light years from the center, roughly 2/3 of the way out along one of the galaxy's spiral arms. When you look at the night sky and see the faint, milky band of light that gives the galaxy its name, you are looking along the plane of this disk, seeing the accumulated glow of billions of stars too distant to resolve individually, their light blending into a soft, luminous river that arches overhead. Every star you can see with your unaided eyes belongs to this galaxy. Every constellation, every familiar pattern in the sky, is a tiny local arrangement of nearby suns within a structure so much larger that the mind cannot truly hold it. The Milky Way contains somewhere between 100 billion and 400 billion stars. The range is wide because counting stars in a galaxy you are inside of is exceptionally difficult. Dust and gas obscure large portions of the disk, and many stars are too faint or too distant to detect individually. But even the lower estimate is staggering. 100 billion stars. If you could count one star per second without sleeping, without pausing, it would take you more than 3,000 years to reach 100 billion. And the galaxy is not alone. It belongs to a small collection of galaxies called the Local Group, which includes the Andromeda Galaxy, a spiral galaxy similar in size to the Milky Way, located roughly 2.5 million light-years away. When you look at Andromeda, if you can find its faint smudge of light in a dark autumn sky, you are seeing light that left that galaxy before the genus Homo existed on Earth. The photons arriving at your eyes tonight began their journey when our ancestors were still millions of years away from anything resembling a modern human. 2.5 million years of travel at the fastest speed the universe allows, and Andromeda is still considered a near neighbor. Beyond the Local Group, the distances multiply with a kind of serene relentlessness. The nearest large galaxy cluster, the Virgo cluster, sits roughly 54 million light-years from Earth and contains more than 1,000 galaxies. Further still, the Coma cluster lies around 320 million light-years away. And beyond these, in every direction, the universe continues. Clusters and superclusters of galaxies strung along the filaments of the cosmic web, separated by voids that stretch for hundreds of millions of light years. The observable universe, the volume of space from which light has had time to reach us since the cosmos began, spans roughly 93 billion light years in diameter. Within that volume, an estimated 2 trillion galaxies exist, each one home to billions or hundreds of billions of stars. The total number of stars in the observable universe is a figure that exceeds anything the human mind can meaningfully process. Something on the order of 200 billion trillion. Written as a numeral, it would be a 2 followed by 23 zeros. And this is only what we can see. The universe almost certainly continues beyond the observable horizon, perhaps infinitely, in ways we cannot measure and may never know. The distances involved are so extreme that they create a kind of natural time machine. Because light travels at a finite speed, looking across space is identical to looking back in time. The sun's light takes about 8 minutes to reach the Earth, so when you see the sun, you are seeing it as it was 8 minutes ago. The light from Proxima Centauri shows you that star as it was 4 years ago. The light from the center of the Milky Way shows you the galaxy's core as it appeared 26,000 years ago, when humans were painting on cave walls and the last ice age still gripped much of the northern hemisphere. The light from Andromeda shows you a galaxy as it existed 2.5 million years in the past, and the light from the most distant galaxies ever observed has been traveling for more than 13 billion years, showing us the universe when it was still in its infancy, a fraction of its current age, filled with small, irregular galaxies still in the process of forming. This leads naturally to the question of how old the universe actually is, and the answer, as precisely as current measurements can determine, is roughly 13.8 billion years. That number has been refined over decades of observation, using multiple independent methods that converge on the same value. The expansion rate of the universe, the temperature and pattern of the cosmic microwave background, the ages of the oldest known star clusters, all of these point to a cosmos that began approximately 13.8 billion years ago in a state of extraordinary density and temperature, and has been expanding and cooling ever since. 13.8 billion years. It is a figure worth sitting with, because it defines the frame within which everything has happened. Every star that has ever shone, every galaxy that has ever formed, every planet that has ever coalesced from a disk of gas and dust, all of it fits within this span. The universe is old, but it is not infinitely old. It had a beginning, and the story of everything that exists has been unfolding within a finite, though staggeringly large, window of time. To place this in perspective, consider the age of the sun. Our star formed roughly 4.5 billion years ago, about a third of the way through the universe's current age. The Earth formed at approximately the same time, condensing from the disk of gas and dust that surrounded the young sun. For the first several hundred million years, the planet was molten and violent, bombarded by debris left over from the solar system's formation. Gradually, it cooled. Oceans formed. And at some point, perhaps as early as 3.8 billion years ago, the first simple forms of life appeared. For the next 3 billion years, life remained microscopic, single-celled, and invisible to any casual observer. Complex multicellular life did not emerge until roughly 600 million years ago. Dinosaurs appeared around 230 million years ago and vanished 66 million years ago. The genus Homo, the lineage that includes modern humans, arose only about 2.5 million years ago. Anatomically, modern humans have existed for roughly 300,000 years. Recorded history, the era of writing, cities, and accumulated cultural memory, spans only about 5,000 years. And the era of modern science, in which we have begun to understand the age and structure of the cosmos, is barely 4 centuries old. If you compressed the entire history of the universe into a single calendar year, with the Big Bang occurring at midnight on the 1st of January, the story unfolds with a patience that makes even geological time feel brief. In the first moments of January the 1st, the universe is a hot, formless fog of radiation and particles. No stars exist, no light travels freely. Within minutes, the cosmic microwave background, that ancient afterglow we discussed, is released as the universe cools enough for the fog to lift. For days afterward, space remains dark. Then, around the 10th of January, the first stars begin to ignite. Enormous, brilliant pioneers burning in a cosmos that has never seen starlight before. Their lives are short, they explode, scattering the first heavy elements, and from their remains, new stars and the earliest small galaxies begin to form. Through February, March, and April, galaxies assemble and grow. The cosmic web takes shape. Supermassive black holes develop at the centers of the largest galaxies. Clusters form at the intersections of filaments. By spring on our cosmic calendar, the universe is already a busy and structured place, but our corner of it does not yet exist. The Milky Way is still growing through mergers and accretion, gathering smaller galaxies into its expanding disk. The Sun and Earth do not form until early September, 4.5 billion years ago, which on this compressed timescale means more than 8 months have passed before our world even appears. For weeks after that, the young Earth is battered and molten. The first simple microbial life appears sometime in late September or early October, and for the next 2 months, October and November, the planet is home to nothing more complex than single-celled organisms. The oxygen we breathe does not begin accumulating in the atmosphere until late October, produced by ancient photosynthetic microbes that slowly transform the chemistry of the air and oceans. Complex multicellular life does not appear until mid-December. The Cambrian explosion, that remarkable burst of animal diversity, happens around the 18th of December. Dinosaurs arrive on the 25th and vanish on the 30th. The entire age of mammals, from the disappearance of the dinosaurs to the present, occupies barely more than the final day of the year. The first members of the genus Homo appear on the evening of the 31st of December. Anatomically, modern humans arrive roughly 10 minutes before midnight. The agricultural revolution, the invention of farming, the founding of the first villages, happens about 20 seconds before the year ends. Recorded human civilization, everything from the earliest writing to the present moment, fits into roughly the last 14 seconds. And your entire life, and the lives of everyone you have ever known or heard of, would occupy a span too brief to measure on this scale. Not even a fraction of a second. A flicker so short that no clock could register it. This is not meant to diminish you. It is meant to place you gently within a context so vast that the ordinary worries of a single evening become, for a moment, wonderfully small. The universe has been here for a very long time. It was here before you arrived. It will be here long after. And in between, in this brief, warm moment of awareness that is your life, you get to look up and see it. That is not nothing. That is extraordinary. Of all the matter in the universe, only an unimaginably small fraction has ever been arranged in a way that allows it to wonder where it came from. You are that arrangement. You are atoms that have learned to ask questions. And the fact that those atoms were forged in the hearts of ancient stars, scattered by supernovae, gathered by gravity into a rocky world, and eventually organized into a mind capable of contemplating the cosmos. That is a story worth telling quietly, in the dark, before sleep. The oldest light in the universe is still arriving. It is called the cosmic microwave background, and it is the faint afterglow of a moment roughly 380,000 years after the Big Bang, when the universe had cooled enough for the first atoms to form. Before that moment, the cosmos was a hot, dense fog of charged particles and radiation, so thick that light could not travel freely. It was absorbed and re-emitted almost instantly, trapped in an opaque haze. But when the temperature dropped below a critical threshold, electrons and protons combined into neutral hydrogen atoms, and suddenly the fog lifted. Light was free to travel, and the radiation released in that moment has been traveling ever since, stretched by the expansion of space from its original high-energy glow into the faint microwave hum that fills the sky today. It comes from every direction equally, and it has been journeying for more than 13 billion years. When instruments detect it, they are receiving a message from the earliest moment the universe became transparent, the first light that was ever allowed to travel freely across the cosmos. It is the oldest thing we can observe, and it surrounds us completely, filling every corner of space with a faint warmth just a few degrees above absolute zero. There is something deeply calming about this. The universe began in unimaginable heat and density, but it has been cooling ever since. The cosmic microwave background is a measure of that cooling, a record of the universe's long, slow exhale from a state of almost infinite compression into the vast, quiet expanse it is today. And it will continue to cool. The expansion of space stretches the radiation further with each passing eon, lowering its temperature imperceptibly, drawing it ever closer to absolute stillness. The universe is not rushing toward anything. It is gently settling, the way a deep breath settles when you stop trying to control it. And through all of this, the immense distances, the billions of years, the trillions of galaxies, there is silence. Real, physical, absolute silence. Space is a vacuum. There is no air, no medium through which sound waves can travel. The explosions of supernovae, which release more energy than the human mind can fathom, produce no sound. The collision of galaxies, which unfolds over hundreds of millions of years and involves billions of stars, happens without a whisper. The spinning of neutron stars, the growth of black holes, the slow drift of continents of dark matter across the cosmic web. All of it proceeds in a quiet so total that it becomes, in its own way, the deepest kind of peace. This silence is not the same as emptiness. It is the natural condition of a universe where the distances between things are so great that no vibration can bridge them. The medium that carries vibration on Earth, air, water, solid ground, has no counterpart in the void between stars. In the interstellar medium, atoms are separated by distances so vast that no pressure wave could ever form. In the intergalactic void, matter is thinner still. The universe is full of energy, full of light, full of gravity and motion and change. But it is free of sound. Everything that happens in space happens in silence, and that silence is not a flaw or a lack. It is simply the way the universe is. It is the quiet that has always been there, stretching from the first moment the cosmos expanded to the farthest reach of the observable horizon. When you think about the night sky in this way, not as a spectacle, but as a vast, silent space in which ancient processes unfold with infinite patience, it begins to feel less like something to marvel at and more like something to rest within. The stars are not performing for you. They are simply burning, as they have for billions of years, converting hydrogen into helium, helium into carbon, carbon into oxygen, building the elements of future worlds in absolute quiet. The nebulae are not posing for photographs. They are drifting, collapsing, glowing faintly with the light of newborn suns, doing the slow work of creation without any awareness that anyone is watching. The galaxies are not racing or competing. They are turning slowly, carried by gravity and momentum through a web of invisible structure. Each one a city of hundreds of billions of stars moving together through the dark. And you are here, on a small, warm world orbiting an ordinary star, in a quiet arm of an ordinary galaxy. The atoms in your body, the carbon in your cells, the oxygen in your lungs, the iron in your blood, the calcium in your bones, were all made inside stars that lived and died before this world existed. You are not separate from the story of the cosmos. You are one of its outcomes, a brief, beautiful arrangement of matter that has somehow become aware of itself, lying quietly in the dark, listening to a voice describe the place it came from. Every breath you take draws in atoms that have been recycled through stars, through nebulae, through the interstellar medium, and through the long, slow chemistry of a living planet. Every breath you release sends those atoms back out into the world, where they will continue their journey, perhaps into a leaf, perhaps into the ocean, perhaps in some unimaginably distant future, back into the heart of a star. The universe does not keep anything forever. Stars are born and they die. Galaxies form and they change. Even the cosmic web will continue to stretch, thinning out as the expansion of space carries its filaments further and further apart. In the very distant future, billions upon billions of years from now, the stars will exhaust their fuel, one by one. The massive blue giants will go first, as they always have, burning through their hydrogen in a few million years and exploding outward. The yellow stars like our sun will follow, each one swelling into a red giant, shedding its outer layers and settling into the long, dim twilight of a white dwarf. Over trillions of years, even the smallest and most patient stars, the red dwarfs that have been burning since the earliest ages of the cosmos, will finally consume the last of their hydrogen. Their light will waver, redden, and go out. And with them, the last natural sources of starlight in the universe will be gone. What remains after the stars are extinguished is a cosmos of dark remnants. White dwarfs, no longer warmed by fusion, will continue to radiate the last of their stored heat into the expanding void. But that heat is finite. Over timescales so long they are measured in trillions upon trillions of years, each white dwarf will cool, degree by degree, century by century, until it reaches the same temperature as the space around it. It will become a black dwarf, a cold, dark sphere of crystallized carbon and oxygen drifting invisibly through a galaxy that no longer shines. No black dwarf exists yet anywhere in the universe. The cosmos is far too young for any white dwarf to have cooled that completely. But eventually, they all will, and the galaxy will become a graveyard of dark, silent embers, each one the frozen memory of a star that once lit the sky. Neutron stars, too, will slow their spinning. The pulsars that once swept beams of radiation across the cosmos with clockwork precision will gradually lose their rotational energy, their signals weakening and spacing further apart until they fade into silence. They will still exist, immensely dense, incredibly small, but they will no longer announce themselves. They will drift through the dark like stones at the bottom of a river, invisible and still. And the black holes, those quiet endpoints of the most massive stars, will be the last significant objects remaining. For a long time, they will be the dominant features of a universe that has otherwise gone dark. But even black holes are not eternal. Through a process so faint and so slow that it defies ordinary comprehension, black holes gradually lose mass. This happens through a subtle quantum mechanical effect at the boundary of the event horizon, where pairs of particles flicker into existence, and under the right conditions, one escapes while the other falls inward. The net result, over timescales so vast they are written with exponents reaching 60 or 70 or 80 digits, is that the black hole slowly shrinks. It loses energy, it radiates, not with light or heat in any conventional sense, but with a whisper so faint that the current universe is far too warm and far too young for it to be measurable. But given enough time, and the universe will have nothing but time, even the largest supermassive black holes will evaporate completely. The very last one will release its final quantum of energy into a universe that has expanded far beyond recognition. And then it too will be gone. What remains after that is the most peaceful state the universe will ever know. A vast, cold, almost perfectly uniform expanse of space, still expanding, still stretching, carrying within it a thin mist of the simplest particles: electrons, positrons, neutrinos, photons of unimaginably low energy, all drifting further and further apart. There will be no stars to light the way, no planets to orbit, no eyes to see. Only the quiet aftermath of a cosmos that once blazed with the light of trillions of suns. And then, gently, without violence or drama, let it all go. But that ending is so far away that it belongs to a future beyond imagining. Tonight, the universe is still full of light. Stars are still being born in clouds of collapsing gas. Planets are still forming in disks of dust around young suns. Somewhere, in a galaxy you have never seen, a massive star is approaching the end of its life. And when it explodes, the elements it has forged will drift outward into space and become the raw material for something new. The cycle continues. It has been continuing for 13.8 billion years, and it will continue for billions more. There is no hurry. There never has been. Let yourself rest inside that thought. The universe is patient. It does not rush its stars into being. It does not hurry its galaxies across the dark. It simply allows things to unfold, one moment at a time, across distances and timescales so vast that the very idea of urgency dissolves. You are part of this patience. Your body is made of atoms that waited billions of years inside dying stars before they became part of you. Your breath carries molecules that have been part of oceans, atmospheres, and living things stretching back to the earliest days of the earth. You are ancient material, briefly awake, resting on a world that spins gently through the dark. There is nothing you need to do right now, nothing you need to hold on to, nothing you need to figure out before the morning comes. The stars will still be there when you wake. The galaxies will still be turning. The cosmic web will still be stretching, silently, across distances too vast to measure. And the atoms that make you will still be the same atoms that were forged in the hearts of stars, carried across light years of space, gathered by gravity, shaped by chemistry, and arranged, just for this moment, into someone who can hear these words and feel the quiet that surrounds them. As we come to the end of this journey, let the vastness settle around you like a blanket. You do not need to carry the numbers or the names. Let them fade the way starlight fades at dawn, gently, without resistance. What remains is the simplest truth of all. You are made of the universe. You always have been. And the universe, for all its silence and all its immensity, is not a cold or empty place. It is the place that made you. It is the place that holds you now. And it will go on holding everything, patiently, quietly, without any hurry at all, long after this night has passed. If you enjoyed this journey, I hope you will consider supporting Science into Sleep with a like, a subscription, or a quiet comment whenever you next wake. It helps other restless minds find their way to these stories, and it lets us keep exploring the cosmos together, one gentle night at a time. But there is nothing you need to do right now. If you are still awake and you would like one more journey, there will be another story waiting on the screen, ready to carry you onward. Otherwise, simply rest here, in the calm after the cosmos. Let your jaw unclench, let your shoulders soften, let your breathing find its own slow rhythm, like the turning of a galaxy, like the drift of light across the dark. Let the weight of the day leave your body the way light leaves a dying star. Slowly, gently, and without any resistance at all, feel the surface beneath you, holding you up, the way gravity holds a planet in its orbit, not gripping, not forcing, simply cradling. You are held. You have always been held by the ground beneath you, by the air around you, by the quiet, ancient forces that shaped every atom you are made of. The universe is still out there. The stars are still burning. The clouds are still collapsing. The light is still traveling. And you are right where you need to be. Warm, still, and made entirely of stardust, resting in a silence older than the earth, deeper than the space between galaxies, and softer than the faintest light arriving from the edge of the cosmos. Sleep well, and good night.